All right, welcome to lecture 3.4. I'm going to try something that I might end up regretting because I am recording from home when my wife is here and my children are here. And my wife is having a conversation with a friend on the phone, and my children are wild animals. So, wish me luck here. But you might hear some crazy noises. Anyway, but I have some deadlines I got to make, so we're gonna try this. We're gonna try this out. We're gonna try to record this thing. 3.4. In 3.4, what I want to do is try to tie together what we know about hypothesis testing with what we just learned about confidence intervals in section 3.3. So first of all, just kind of as a summary, this first chart here contains what we know about hypothesis testing. Okay, so nothing new here. What a hypothesis test will tell us is whether or not there's some kind of change or effect or difference in our sample as compared to the hypothesized population or parameter, right, in the null hypothesis. Now, if there is an effect or change or difference, then we'd like to know how big that change, effect, or difference is, right? We'd like to know what the effect size is. And confidence intervals are a way that we can sort of try to estimate how big that change, difference, or effect is. So we learned about constructing confidence intervals in section 3.3. We're going to use the apps from Art of Stat to get both p-values and confidence intervals. And, we've practiced doing that several times by now already. One thing that I haven't really spent a lot of time on, but that deserves some comment, is that technically there are conditions you have to check in order to get these p-values and construct these confidence intervals, because when we are calculating these p-values, it's assumed that, for example, p hat is normally distributed when we're calculating a p-value for the proportion, for a test on a proportion. Or when we're calculating a p-value for a test on a mean, it's assumed that the mean follows student's t-distribution. And there were conditions that you might remember from section 2.8 that had to be met in order for those conditions, in order for those statements to be true, right? So these aren't going to be a big emphasis for me, but yes, if you want to run a one sample proportion test and or construct a confidence interval for the proportion, then these are the conditions that you'd have to check, right? You have to make sure that your sample size is no more than 5% of your population size, and you have to make sure that n times p times q is at least 10. For a one sample mean test, these are the conditions that you have to check down here, right? You have to make sure, again, your sample size has to be no more than 5% of your population size, and your sample size has to be, it either has to be at least 30, or it has to come from a population that's normally distributed. The sample has to come from a population that's normally distributed. So again, I'm not going to take time during the lectures to check those conditions, okay? But just know that, like, in the real world, technically, you'd have to make sure that those conditions are met before you go ahead and run these tests. If the conditions don't pass, right? If one or more of the conditions fails, then the test or confidence interval results you get are not valid, right? Okay, couple notes also. We talked about the level of significance in a hypothesis test alpha. We said this is sort of the cutoff value that we set for ourselves, or rather, it's the cutoff value that the researcher sets before they ever even collect data. And it's how sure we are that we're not rejecting a true null hypothesis, since the p-value has to be less than alpha in order for us to decide to reject the null, okay? We also talked, when we talked about confidence intervals, we talked about the level of confidence, right? The level of confidence is how sure we are that the interval actually contains the parameter that we're trying to estimate. So if you think about those two statements next to each other and squint at them just right, then I think it should make some intuitive sense to you that those quantities are going to be related. And in fact, they are. They're complements of one another, okay? So the level of significance of a hypothesis test is the complement of the level of confidence in a confidence interval, and vice versa. For example, A 5% level of significance corresponds to a 95% level of confidence, okay? So if you're running a hypothesis test at the alpha equals 0.5 level of significance, then the confidence interval that you should construct in association with that hypothesis test would be a 95% confidence interval, okay? 100% minus 5% is 95%, right? Similarly, if you're running a hypothesis test at the 0.1 level of significance, 0.1 is the same as 10%, right? So the corresponding confidence level would be 90%, okay? You could kind of think of it like this is how confident you are that you're not rejecting a true null hypothesis. So in general, an alpha level of significance corresponds to a 1 minus alpha level of confidence, right? They're complements of one another. Okay, and then one last thing that I want to say before we start looking at some examples. If our confidence interval contains the value of the parameter claimed in the null hypothesis, then we really don't have good evidence to reject the null hypothesis, right? So think about it. If you construct a 95% confidence interval for the proportion, and the interval that you construct has the population proportion from the null hypothesis inside of it, then that means that actually that estimate for the estimate from the null hypothesis for that population proportion is a pretty decent estimate because it falls within our confidence interval, and therefore we would not reject the null hypothesis. Same thing goes for a mean, right? So what that means when we're connecting confidence intervals to hypothesis tests is that if we get a large p-value in our hypothesis tests, then we're going to decide not to reject the null hypothesis. And what that means is that the null value, right, the value from the null hypothesis is probably inside of our confidence interval. And then conversely, if we get a small p-value, that means that we're going to reject the null hypothesis. Then what that means is that the null value is probably going to fall outside of the confidence interval. So I want to walk through several examples, and we'll kind of relate these things together. If that was confusing to you, hopefully it'll become more clear as we proceed through the examples. So I've got 4 examples for you in this section. Let's get to it. So this first one says, in 1966, support for the death penalty was at an all-time low with around 46% in favor. In April 2021, a Pew Research poll asked 5,109 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 3,002 were either somewhat or strongly in favor. And then part A asks, have people's feelings about the death penalty changed since 1966? And we're supposed to test at the 0.05 level. Okay, so the first thing we should do is decide what our null and alternative hypotheses are, which in this case is going to require us to figure out if we're testing a mean or a proportion so that we can run the correct test. Now, one way that you can decide whether you're testing a mean or a proportion is just by thinking about the data that were collected. If they were categorical, then chances are we're going to be running a test on a proportion. If they were numerical, then chances are we're going to be running a test on a mean. So in this case, if you think about what the researchers did, they went out and asked people, are you in favor of the death penalty? And the answers that people gave were yes or no. Or maybe it was like strongly in favor, somewhat in favor, somewhat opposed, strongly opposed, right? Something like that. But either way, those responses are not numerical, they're categorical, which means we're most likely testing a proportion here. And indeed, another way to see this is, well, we went out and asked this number of people their opinion, and then this number of people answered a certain way. Clearly, we want to know what percentage of people answered that way, right? So a percentage is basically the same as a proportion, so we're testing proportions here. All right, so the null hypothesis is that P equals something. Well, what we want to know is if people's feelings have changed since 1966, right? Well, how did people feel in 1966? Well, the first sentence says, in 1966, support was at an all-time low with 46% in favor. So in 1966, the proportion of people in favor, P, was equal to 0.46. And if people's feelings have not changed, then P would still be equal to 0.46 today, right? So that's our null hypothesis. The alternative hypothesis is that their feelings have changed. that p is no longer equal to 0.46, right? P does not equal 0.46. So there's step one. For step two, we need to calculate the sample proportion, p hat. Right? Since we're testing a proportion, the evidence would be a sample proportion. And in this case, there were 3,002 people in favor out of 5,109 people surveyed. So we can type that into the calculator and see what we get. And that comes out to about 0.588. Ooh, let me write that better. 0.5. That's still bad. It's hard for some reason on the on an iPad. 588. I always write so sloppy on an iPad. But there you go. Okay. I don't know why I boxed it, but whatever. There's the sample proportion. That is quite a bit different from 46%. I would be surprised if we didn't reject the null hypothesis. I think we most likely will. But there's only one way to be sure, and that is to actually run the test. Since we're testing a proportion, we're going to go to inference for a proportion. We're going to enter 5109 for the sample size and 3002 for the number of successes. And then we'll see what we get for the p-value. So let's head over to Art of Stat. Okay, web apps, scroll down. I'll keep going. Here we go, inference for a proportion. I have the number of successes here. Okay, so it was 5109 and 3002. And I don't want a confidence interval just yet, although I think I'm going to be asked for one later. The null value was 46%. And I do want a two-sided test, so I'm just going to leave it two-sided here, right? My alternative hypothesis matches what I wrote down on, on my paper a second ago. And yeah, sure enough, my p-value is really small, less than 0.0001. Okay, it's so small that Art of Stat won't even tell me what the exact value is. It's just saying, well, it's smaller than 0.001, right? Very small. So decision 0.0001 is less than 0.05. So reject the null. We're rejecting the null in favor of the alternative, right? We're getting rid of that guy, so that means the alternative must be true. There is sufficient evidence to conclude that people's feelings about the death penalty have changed since 1966. Okay, so there's our hypothesis test. Now part B says, construct and interpret a 95% confidence interval for the proportional, okay, etc. Let's just go back to Art of Stat. Okay, so heading back over to Art of Stat, all we need to do is change it back to a confidence interval. And we do indeed want a 95% confidence interval, so that's already set up. And so there it is, right? I'll round this to 3 decimal places, so I'll just call it 0.574 to 0.601. Okay, so there's my interval. We were asked to interpret it as well, so we could say something like, we are 95% confident that between 57.4% and 60.1% of people are in favor of the death penalty. Okay. We were also asked to comment on how your confidence interval relates to the results of the hypothesis test. Well, with our hypothesis test, the null hypothesis was that p equals 0.46. But as you can see, 0.46 is way outside of our confidence interval. So we strongly suspect that this is not the case, right? Because 0.46 is not in here, right? So that's how, and by the way, that corresponds perfectly with our rejection of the null hypothesis in our hypothesis test, right? So so we could say, well, 46%, so this is like a separate thing now, right? But 46% is nowhere near our confidence interval. So the results of our hypothesis test are verified. Okay. All right, part C, comment on the statistical and practical significance of the results of this study. Okay, so in the previous section, we learned that statistical significance is measured by the p-value, basically, right? Like if you reject the null hypothesis, then the results are statistically significant, right? And that's what happened here, okay? So this result is definitely statistically significant. Practical significance is a little bit more slippery, right? The idea behind practical significance is, okay, yeah, sure, there was an effect, but how big was the effect? In this case, I would say, just looking at our sample proportion compared to the null value, that's like a 12% increase, right? So I would say, yeah, that's a huge, that has huge practical significance. So the results are statistically significant because we rejected H null. They're also practically significant because the difference between 0.46, which was the null value, and 0.588, which was the sample proportion, is large. Okay, that's a large difference. When you're talking about proportions, right? Remember, proportions are always between 0 and 1. So this is like 46% versus almost 59%, right? That's a huge difference. That's a huge difference. Think about if you had a ballot measure or something that was asking about, the death penalty. Well, at 46% of people in favor, that measure would fail. At almost 59%, the measure would pass, right? So there's a huge practical significance there. Alrighty, moving on. According to the American Time Use Survey, the typical American spends 67.8 minutes per day watching television. Do TikTok users spend less time each day watching television? A survey of 150 TikTok users resulted in a mean time watching television per day of 63.3 minutes, with a standard deviation of 16.5 minutes. Part A. Determine if TikTok users spend less time watching television at the 0.01 level of significance. Okay, so again, the first order of business is to figure out what test we're running. Are we testing a mean or are we testing a proportion? Now, in this case, if you went out and you actually surveyed 150 people and said, how long do you watch TV every day? People aren't going to say green, right? They're not gonna give you a category. They're gonna give you a number. You say, how long do you watch television? And they're gonna say, oh, 45 minutes, right? But they give you a number. So we have numerical data here. That means that most likely we're testing means. And another kind of dead giveaway is that, we're talking about means and standard deviations and stuff. So clearly this is all numerical, right? We're going to be testing a mean, mu. The null hypothesis is that people who use TikTok spend the same amount of time watching television as people who don't use TikTok, right? Which is 67.8 minutes, right? 67.8. The alternative, well, we want to know if they spend less time. So mu less than 67.8. Step 2 would be to calculate the sample mean, which in this case was just given to us. We were told the mean time watching television per day was 63.3. So x bar equals 63.3. That is indeed less than 67.8. Is it a lot less, right? Is it statistically significant? Well, the only way to know that is to run the test. So we're going to use inference for a mean, and we'll enter the sample mean. We'll enter the sample standard deviation, 16.5. We'll enter the sample size, 150. And then doing all of that, we should be able to get a p-value. So let's head over to Art of Stat and see what we get. So I don't want inference for a proportion anymore. Let's open up the inference for a mean app. And I have some summary statistics that I can enter here. The sample size we said was 150. The sample mean we said was 63.3. And the sample standard deviation we said was 16.5. I don't want a confidence interval just yet. I want to run a significance test. The null value was 67.8, right? Because the null hypothesis said mu equals 67.8. And I don't want a two-sided alternative. I want to test to see if TikTok users spend less time, right? So now this alternative should match what I wrote down on my paper. I've got a p-value of 0.0005. Okay, 0.0005. And that is good enough, I think, to reject the null hypothesis, right? 0.0005 is indeed less than 0.01, so we reject H null. Okay, since we're rejecting the null, that means there's evidence to support the alternative, right? There is sufficient evidence to conclude that TikTok users spend less time. We'll just say that they spend less than 67.8 minutes watching TV per day. Okay. So then, so that's the result of the hypothesis test. Part B says, what does the p-value mean in this scenario? Ooh, okay, good question. What does the p-value mean? We got a p-value of 0.0005. That is the probability of obtaining this sample mean if the null hypothesis were true. Okay, so if we assume that TikTok users spend 67.8 minutes watching TV, then there is a 0.0005 probability of obtaining a sample of 150 TikTok users with a sample mean of 63.3. So if we assume that the population mean time watching TV for TikTok users is 67.8 minutes. Then there is a 0.0005 probability of obtaining a sample mean of 63.3 minutes or less. Okay, in math symbols, what we would say is, well, the probability that x bar is less than or equal to 63.3, given that mu equals 68.7, equals 0.0005, right? That's the p-value. All right, part C, construct a 99% confidence interval. Let's see. Okay, so once again in Art of Stat, the only thing I need to do is change the type of inference from a significance test to a confidence interval. This time I don't want a 95% confidence interval, I want a 99% confidence interval because I used a 0.01 level of significance in the hypothesis test, right? Here are the values. So I might round this to one decimal place. We'll call this 59.8 and 66.8. So 59.8 to 66.8. We weren't asked to interpret the interval this time. If we wanted to give an interpretation, we could say something like, well, we're 99% confident that the amount of time TikTok users watch TV per day is somewhere between 59.8 minutes and 66.8 minutes, right? So we weren't asked to write down that interpretation, but we were asked to comment on how our confidence interval relates to the results of the hypothesis test. Well, looking at the hypothesis test, the null hypothesis was that mu equals 67.8 minutes. If that were true, then 67.8 should show up inside of our confidence interval, and yet it does not, right? 67.8 falls outside of our interval. So this interval sort of verifies that the results of our hypothesis test were correct because we decided to reject the null hypothesis. And it seems like that's exactly what we should do since 67.8 is not in the interval. So we rejected H null, which was that mu equals 67.8, which seems appropriate since 67.8 is not in our confidence interval. Okay, part D, comment on the statistical and practical significance that using TikTok has on the amount of time people watch TV. Okay, well, it's definitely statistically significant, right? TikTok users spend less time watching TV. As far as practical significance is concerned, well, yeah, they watch less TV, but not that much less. Look at this. We're talking about like a 4-minute difference. I mean, that's just not that much less. So I would say, yeah, it's statistically significant, not very practically significant. What difference does 4 minutes make when you're talking about watching an hour-long show or something? TikTok users spend statistically significantly less time watching TV. However, the difference is not practically significant since there's only about a 4-minute difference, right? And if you wanted, you could say like a 4-minute difference between what the null hypothesis claimed and what the sample evidence indicated, right? So you could say between 67.8 and 63.3, right? Now, I just want to pause here a second and say, like, if you're freaked out by the practically significant thing, like you're still like not clear what it means. Statistical significance is easy, right? If you reject the null, the results are statistically significant. Practical significance is a little bit wigglier, right? It's like as long as you're backing up your answer with good reasoning, you're not going to get marked down. But for me personally, I would say a 4-minute difference when you're already talking about watching TV for over an hour, a 4-minute difference is just not that substantial. So I would not call this practically significant. Yes, there's a difference, but it's not really a substantial difference. Okay. Let's look at another one. According to the MAA, that's the Mathematical Association of America, 1% of bachelor's degrees in the United States are awarded in the fields of math and statistics. A recent math graduate collects a simple random sample of 12,317 recent college grads and finds that 131 graduates majored in math or stats. Part A, does the evidence indicate that the percentage of bachelor's degrees awarded in the fields of math and stats is actually greater than 1%? Use a 0.05 level of significance. Okay, well, I'll let you pause the video and see if you can figure that out. Okay, here's my solution. So we're definitely going to be testing proportions, right? We want to know if the percentage is blah, blah, blah. Well, that's the same as a proportion. The null hypothesis is that, no, the proportion is the same, right, as what the MAA claims, 1%. The alternative is that it's greater, right? This is what the student thinks, okay? The sample evidence in favor of this is that 131 out of 12,317 graduates completed a bachelor's degree in math or statistics. So if we punch that into our calculator, we get approximately 0.011. Okay, so that is indeed bigger than 1%, right? It's 1.1%. So slightly bigger, right? Ever so slightly bigger. Not substantially though, right? Okay, but maybe it's statistically significant just because we had such a large sample size. So there's only one way to know that, and that would be to run the test. So we're going to go to inference for a proportion. We're going to put in 12,317 for the sample size and 131 for the number of successes. And then we'll get a p-value out of that. So let's see. So inference for a proportion. Sorry, 12,317 for the sample size, 131 successes. We want a significance test where the null value is 1. And we want to run this right-tailed. We wanted to see if the proportion was bigger. And we get a pretty large p-value, 0.2391. Now, looking ahead, I know that I'm going to want to get a confidence interval as well. So I'll come back and change this to confidence interval in a second. Let's write down our p-value, then we'll come back and we'll change it to a confidence interval. Okay. All right, let's construct our 95% confidence interval while we can. So I'll change this from a significance test to a confidence interval. And there we go, 0.009 to 0.012. Okay. Okay, filling out the rest of this. Let's see. Step 4 up here with the hypothesis test, I want to make my decision. 0.2391 is not less than 0.05, which was my level of significance in this case. So do not reject H null. Since we're not rejecting the null hypothesis, that means there's not evidence to support the alternative, right? There is not sufficient evidence to conclude that the proportion of degrees awarded to math and stats is greater than 1%. Okay, part B, what does this p-value mean in this scenario? Well, it means that if we assume the proportion is 1%, then there's about a 23.9% chance of obtaining a sample proportion of 1.1%. 23.9% chance is not very small, right? So it's certainly not small enough to cast any doubt on our null assumption, or on our null hypothesis, which is why we don't reject it, okay? If we assume that p equals 0.01, then there is a 0.2391 probability of obtaining a sample mean of p hat equals 0.011 or more. So there's the explanation in words. In math symbols, we might say something like this, right? Probability that p hat is greater than or equal to 0.011, given that p equals 0.01, equals 0.2391. And that's our p-value. Part C, construct a 95% confidence interval. Okay, done. Now it says you don't have to write an interpretation for the interval, but comment on how your confidence interval relates to the results of the hypothesis test. Well, what this interval means is that we are 95% confident that the true population proportion of bachelor's degrees awarded to math and stats is somewhere between 0.9% and 1.2%. Notice that our null hypothesis falls inside of that interval, and therefore there's no reason to suspect that the null hypothesis might be false. So we do not reject it. Okay, so once again, this confidence interval supports the results of the hypothesis test, right? So 1.1, or sorry, not 1.1%, just exactly 1% was the null hypothesis. Maybe I'll say that, right? H null was that p equals 0.01, right? This is within our 95% confidence interval. So there's little reason to suspect that H null might be false. Hence, we did not reject H null. Okay, part D. Comment on the statistical and practical significance of these results. Well, we didn't reject the null hypothesis, so the results are not statistically significant. The results are not statistically significant since we did not reject H null. They also wouldn't be practically significant. I mean, let's just pretend for a second that we had rejected the null hypothesis. Still, the difference here is going from 1.1% to 1.1%. That's just not a large difference. So it wouldn't be practically significant even if we had rejected the null. They are also not practically significant. I'll just leave it at that. But yeah, they're not practically significant. In your notes for your own benefit, you might want to write down why we're saying that, right? You might want to say something like, they're not practically significant because there's just not much of a difference between 1% and 1.1%, right? Okay, part E. Do you think there's actually a difference here and we just need a larger sample size to show it? Or do you think there's just not a difference? Well, recall that our sample size was 12,317. That's a huge sample size. So I don't think sample size is the issue here. I think it's just that there's just really not a difference, okay? Sample size is not an issue here. I think there's simply not a difference to detect. Okay. So that'll do it for that one. One more example. It says among individuals who had credit cards in 2022, the mean number of credit cards was 3.5. A small credit union in Tulare County, California felt that its customers have fewer credit cards than that. They looked at a random sample of 5 of their customers and found a mean of 2.5 cards and a standard deviation of 1.3 cards. Assume that the number of credit cards a person owns is normally distributed. Part A. Do the results of the credit union survey imply that the mean number of cards held by their customers is less than 3.5? Go ahead and pause the video, see if you can run that test. Here's my solution. We're definitely testing a mean here, right? We were told point blank, right, to test whether the mean is whatever. We want to know if the mean is less than 3.5. Well, the null hypothesis would be no, it's equal to 3.5, right? And then the alternative is that, yes, it's less than 3.5. What sample evidence do we have? Well, in our sample of 5 individuals, the mean was 2.5, which is 1 full credit card less, right? Now, to me, that seems like a substantial difference. However, our sample size was tiny. It was tiny. So we'll have to compute the p-value to see if it was enough, but I kind of feel like it's probably not going to be because our sample size was just so small. Only one way to find out. We'll run inference for a mean. We'll put in x bar equals 2.5, s equals 1.3, and n equals 5. And we'll see what we get for a p-value. Okay, done with the inference for a proportion. I want to run inference on a mean. We've got some summary stats. Sample size was 5. Sample mean was 2.5. Sample standard deviation was 1.3. And the null value was 3.5. We wanted to test mu equals 3.5 against mu less than 3.5. Okay. And sure enough, right? Like 2.5 is really, there's a big difference there, but it's just not quite enough because I think it's because we had a small sample size. So we get a p-value of just 0.0803. And then part B wants a confidence interval. So let me go ahead and write that down while I'm here in Art of Stat. We'll change significance test to confidence interval. And yes, we want a 95% interval, so this is it, right? So 0.8, let's just round to one decimal place here. We'll say, so 0.9 to 4.1, 0.9 to 4.1. Okay, and now let's fill in the rest, right? So, decision. 0.0803 is not less than 0.05. So do not reject. H null. Conclusion. Well, we're not rejecting the null hypothesis, so there's not sufficient evidence to support the alternative. Okay, so there's not sufficient evidence to conclude that the mean number of cards at this credit union is less than 3.5. Here's where the wording of this conclusion really matters, because I personally, I would say, I don't think it's that there isn't a difference here. I just think we didn't have enough evidence to prove it, right? So that's why we word these conclusions the way that we do. There's just not sufficient evidence, right? Here's our confidence interval that we already wrote. This time we were asked for an interpretation. So let's give an interpretation. We are 95% confident that the true population mean number of credit cards at this credit union is somewhere between 0.9 and 4.1. Okay, part C. Comment on the statistical and practical significance of these results. Well, we didn't reject the null, so the results are not statistically significant. Okay. However, pretending for a second that we had rejected the null hypothesis, I would say that 3.5 compared to 2.5 is a pretty significant difference. I know you might be thinking, well, that's only one credit card less, and that's true, but we were only starting with 3.5 credit cards to begin with, right? So you decrease by one, and that's a pretty significant amount. If we were talking about on average, people have 200 credit cards, and in our sample, we got 199 credit cards, per person. That would not be a significant difference, right? But when we're talking about we're only starting with 3.5 credit cards to begin with, then when we decrease by one, that's a significant amount. And I think that we just didn't have enough evidence to show it, right? So the results are not statistically significant. That's probably a sample size issue. So I would say, however, I don't know why I changed colors, but so be it. However, if we had rejected H null, then I would say a one credit card difference is practically significant since we were only talking about 3.5 credit cards to begin with. And that leads us into part D, right? Do you think there's actually a difference here and we just needed a larger sample size to show it? Or do you think there's just not a difference? I absolutely think that this is just a sample size issue. Now, just to be clear, it is possible that because we had a small sample size, we're getting some really skewed results, right? And that's exactly why we have to be careful and not just look at the sample mean and say, well, yeah, clearly the sample mean is showing a difference. We have to actually run the test and see, do we have sufficient evidence to say that? Okay, but with that said, assuming that we had a sample size that was, 20 times as big, if we got the same sample mean, we would certainly be rejecting the null hypothesis. Okay, so yes, I think that this was a sample size issue. So I think that there's a difference but we just didn't have a large enough sample size to show it. Okay. Questions like part D really require a lot of careful thought, okay? Because the same thing could be true in the other direction. It might be that you have a small sample size and so you get a really strange result just by luck of the draw, okay? And so that might cause you to reject a null hypothesis when you really shouldn't. If you got a larger sample size, you would see that, there's really not as much of a difference. It's just that by random chance we happen to get 5 really extreme, values in our small sample size. All of this to say that small sample sizes cause problems. And so we should try to get larger sample sizes when we can. Okay. I want to give you a little bit of a bonus section here. Talking about how technology constructs confidence intervals. I think we finally have enough understanding and notation to talk about this. We began this discussion in the previous section where we talked about how the way that technology constructs a confidence interval is that it first calculates a point estimate, which we already know how to do, and then it calculates a margin of error, which we don't know how to do. But the way it gets its interval is that it takes the point estimate and then it adds and subtracts the margin of error. So the question that we want to answer now is, okay, how does technology determine the margin of error that it needs? So for example, if I want to be 95% certain that my confidence interval contains the population parameter, how big does my margin of error need to be so that it can capture that level of confidence? And so there are 2 separate results, one for the proportion here and then one for the mean down here. And I'm not going to prove the result for the mean, but we can look at the proof for the result for the proportion. The proof for the mean is similar, okay? So just looking at the proportion, the case of the proportion, the way that technology is going to compute our confidence interval is going to get our sample proportion, right? Our point estimate, and then it's going to add or subtract our margin of error. Now, looking at our margin of error, this value right here, the z sub alpha over 2, that represents the z-score whose area to the right is alpha over 2. In other words, it's the marker where alpha over 2% of the data falls above that marker, okay? It's the number of standard deviations that lands us in this spot. So then we multiply that by the value of a standard deviation so that we actually figure out where that value lies in the distribution, okay? And then we take that and add it to our sample proportion to get to this side of things. We can also subtract it from the sample proportion to get to this side of things. And why alpha over 2? Why do we want these tails to have alpha over 2% of the data? Well, because when you add alpha over 2 plus alpha over 2, you get alpha. Okay, and so that means you will be 1 minus alpha percent confident that the true population parameter is within this region. Okay. So that's all I'm really going to say about this. The details are written here for you. And of course, there's a little bit of algebra that goes into actually taking that and getting a confidence interval for the proportion rather than a confidence interval for the sample proportion. But I'll let you read through that on your own. But this is what technology is doing behind the scenes when it calculates a confidence interval. And we could do these things by hand if we wanted to, but we don't. So we'll let technology do it for us. But anyway, this is what technology is doing. This is why it's doing that calculation. Okay. And so now you know, and you don't have to just assume that it's magic going on behind the scenes, right? There is actual mathematics going on here, and this is the reason. Again, you've got a similar result for the mean. This is the calculation that technology is performing, and something similar to this is why it's performing that calculation. But that's it for this section. So moving forward, we're going to look at two sample hypothesis tests and their corresponding confidence intervals. So I will catch you in the next section when we talk about that topic.